Wonderful.
Good afternoon, everybody. My name is Sergey Luchkin, and in this presentation, I will show you our attempts to understand mechanism of electrochemical activation of overlithiated lithium-rich NMC. So I'll start with a short introduction of lithium-rich NMC, and then we'll show you our experimental results with short conclusion in the end. So let's start. Lithium-rich NMC belongs to a family of transition metal oxide materials, transition layered metal oxide materials, famous member of which are lithium cobalt oxide and NMC, which are currently employed in lithium-ion batteries. And its development was fueled by partial substitution of transition metals with lithium. And this small trick allowed to increase capacity to a large extent, thanks to activation of additional anionic redox. But despite this great increase in capacity, this material is not on the market yet because it has a number of serious drawbacks. But here I want to focus on a very specific phenomena, which is called electrochemical activation. And this phenomenon is observed when we keep adding more lithium into the structure. And when lithium to transition metal ratio exceeds 1.5, we start to observe this strange behavior when during cycling, capacity increasing upon cycling. And this is highly unusual. There were several hypotheses proposed to explain this phenomena, but none of them seems sufficiently solid. So we tackled this problem, and here are our results. So we prepared several sets of powders, and here you can see a same image of two powders. One is stoichiometric, which doesn't show activation process, and another is overlithiated with activation. They were characterized by X-ray diffraction, and here are very sharp XRD patterns indexed in monoclinic symmetry with typical superstructure for NMC, and superstructure peaks are a little bit more intense for overlithiated case. We also performed inductively coupled plasma mass spectrometry in order to determine exact composition and lithium to transition metal ratio, as you can see in this table. And we performed titration to measure valence states of D metals. And as expected, in the overlithiated case, it was higher. But unfortunately, titration cannot discriminate individual oxidation states of D metals. So we are currently running yields experiments to refine oxidation states of nickel, manganese, and cobalt. These powders were used to assemble cathodes, which were to prepare cathodes, which were assembled into one cells. And they were cycled versus lithium at different C rates. And here you can see two examples of cycling at 0.1 C rate. So top is for stoichiometric sample without activation. And on the bottom, we can see cycling of the overlithiated sample with distinct activation process. But here I want to focus your attention on the very first charge curve. And on the stoichiometric sample, we can see two intensive peaks. First relates to oxidation of transition metals of nickel and cobalt. And the second relates to oxidation of oxygen. And starting from the second cycle, it delivers full capacity. While in the overlithiated case, the first peak is very subtle, so transition metals are almost not oxidized. And the following oxygen oxidation is less intense than in the stoichiometric case and shifted to high potentials. So we disassembled these cells, extracted cathodes, washed them, embedded in epoxy and polished, prepared cross sections, and characterized them by atomic force microscopy and Raman microscopy. Here you can see examples of AFM topography, surface potential, conductive AFM, and the Raman chemical map, which correlate quite nicely. And here are comparison of fresh and partially activated samples of overlithiated lithium-rich NMC. A fresh sample on the left-hand side and partially activated on the right-hand side. It was activated to 150 milliamp hours per gram out of 280 theoretically possible. And we can see a distinct core shell structure in all channels. So in topography, you can see a flat core, flat shell, and slightly convex core. And this core is harder. We measured it as well. This core is also more conductive, which is attributed to presence of mixed valence state of nickel and cobalt in high oxidation states. And core also has a lower surface potential, which corresponds to larger work function. And the shell has higher surface potential and smaller work function. And if you look at this density of state sketch, you can see that a larger work function corresponds to the case when lower oxidation states of transition metals are not occupied, while when smaller work function, which corresponds to the shell case, there's lower oxidation states of transition metals are occupied and they're available for reversible redox. So there is also the same core shell structure on Raman map, and here a bit more details. We actually measured many samples with Raman, both overlithiated and stoichiometric after different cycling regimes, and a number of reference samples. But what is important here is that EG and A1G peaks of overlithiated sample, fresh, this black line, they're blue shifted as compared to the stoichiometric sample, which means that transition metal oxygen bond is stiffer. That implies that transition metal are in high oxidation states. And after partial activation, we can see this core shell structure, and in the core, this red spectra resembles fresh spectra, which is not activated, well, slightly less intense. While in the shell, this green spectra closely resembles stoichiometric case, which is active. And we can see that well, while in the non-active case, except for blue shift, there is additional peak in the middle, which is ascribed to presence of nickel 3+, and there is highly intensive EG peak, which we have not explained yet. But the intensity of EG after activation dropped a lot, and this nickel 3+ attributed peak has vanished. We also cut lamella using focused down beam from the same particles that we measured by AFM and Raman, and performed electron microscopy. But since we are short in time, I will show you only relevant results to what we studied. And this is refinement of oxidation states of individual transitional metals. So we refined oxidation states of manganese before and after activation, and in the fresh state before activation it was in 4+, and after activation it became 2.4+. And now we are refining oxidation states of nickel. These measurements, well, this study is not finished yet, but based on the data that we have, I can propose the following mechanism of electrochemical activation. So initially, transition metals are in high oxidation states in this material, in overlithiated Atomic NMC. And when we start this first charge, then they are not oxidized because there is no room for oxidation. They are already oxidized to high oxidation states. And it results in, so lithium is not deintercalated, and this somehow hinders oxygen oxidation, which still happens at the very surface of the particle, because at the surface, transition metals are slightly reduced as compared to the bulk, and there are also a large number of uncompensated bonds and defects, so oxygen oxidation still goes on. And during the following discharge, transition metals are reduced in this layer where oxygen was oxidized, because as you can see on this differential capacity plot, oxygen is reduced during this discharge at high potential and at low potential. So there is a window for a reduction of transition metals. During the second charge, transition metals that were reduced before they are oxidized, oxygen is oxidized in this very shell part of the particle, and a new set of oxygen is being oxidized at the interface between this active part outside and non-active part inside. And during the following discharge, a new set of transition metals is reduced So we can see formation of this active core around non-active shell. And so this is a mechanism of electrochemical activation that we deduced so far. So let me conclude. We used correlative AFM, Raman, and STEM to study activation of overlithiated lithium-rich NMC. And activation starts at surface and proceeds towards center via core shell structure. And based on the data we have, it seems that high initial valence states of d metals hinder lithium deintercalation and oxygen oxidation, but exact details are still being refined. So thank you for your attention.